So here's lesson 3 that we'll be working on for this video, and I'm going to divide this up in lesson 3 up into 2 different videos, but the objectives for lesson 3 are identify the Bronsted-Lowry base, conjugate acid or base, given the pKa values, predict relative acid strength. Number 3, looks like there's 2 number 3s here, huh? Number 3 is identify types of organic acids. The next number 3 is using electron pushing arrows, show the step-by-step mechanism, and finally draw the calculated condensed and structural and skeletal structures of a given product. So we're going to do, I think, the first 2 here for this first video. The first one again is identify a Bronsted-Lowry or Lewis acid or base. Okay, so the first thing we have to do is just identify a Bronsted-Lowry acid or base. Well, Bronsted-Lowry acid or base is a proton donor or a proton acceptor. I'm going to do it like that. Okay, where can you see I've got a hydrogen that's sort of out to the side, and if these electrons come over here and hit that, and those go there, this becomes that. And can you see how this B has picked up an extra proton by doing that? Okay, so then this is a Lewis acid. Oh, sorry. A Bronsted-Lowry acid or a Bronsted-Lowry base. Okay. And so since this is the guy that can donate a proton, that's going to donate a proton in this story, he's going to donate a proton, then he's the one who has donated his proton. This is consequently going to be the Bronsted-Lowry conjugate base. Okay, so the term conjugate means the base that's applied that comes from this acid. Okay, that is everything except the proton. So a conjugate base is always going to be this acid minus the proton. Okay, I mean unless it's a Lewis, that's a little bit different. Okay, so Bronsted-Lowry acid is something that donates a proton. A Bronsted-Lowry base is something that accepts a proton. So can you guess what the conjugate base is going to be? Of course, it's going to be the base accept plus a proton, right? Bronsted-Lowry conjugate base. Okay, we'll do an example in just a second. Now let's talk about Lewis. That's Bronsted-Lowry. Probably 2 dots over that, maybe, I don't know. And then Lewis. Okay, a Lewis acid or base is, I guess, the classic example of a Lewis acid is something that accepts protons. And a Lewis base is something that, accepts electrons. I mean, I keep saying these things backwards. Hopefully you get these terms in front of you. So this is something that donates electrons. This is something that accepts it. Do you remember why boron accepts electrons? Why does boron accept electrons? That's a good question. Please think about that. Why does boron accept electrons? And I'm not going to tell you here in this video, but I want you to think about it. Okay? So what's going to happen here? These electrons go boom and hit that. Okay? And what's the product of this then? It's boom, boom, boom. And there's a formal charge on that and a formal charge on that. I should have given you a chance to say what those formal charges are. Okay, so this is Bronsted-Lowry. This is Lewis. I just gave you an example of Lewis, but I haven't given you a real example of Bronsted-Lowry. This is sort of the general terms. But let's talk about a general Bronsted-Lowry acid and base. HOH. This is really H2O, but I want to put the H out to the side so we can see it. It's just H2O, same thing. Okay? And this is, let's say, ammonia. Okay, I used ammonia up here for a Lewis base, by the way, and I used ammonia for a Bronsted-Lowry base here. Which is it? Which is it? Bronsted-Lowry or Lewis? Okay, that's a question I want you to answer tomorrow in class. Alright, so this ammonia then goes here, boom. These electrons, boom. Okay. And what's the product of that? Actually, I want you to predict the products for this. That's another question I want you to answer. Give me a lot of questions in this video today. Alright, so that's objective number 1. Objective 1 was identify a Bronsted-Lowry or a Lewis acid or base and its conjugate base and acid in a reaction. Okay? Number 2, objective number 2, lesson 3, objective 2, is given a pKa value, predict the relative acid strength. Okay, so let me remind you about something that we learned in Gen Chem. We learned that if we have A plus B in equilibrium with C plus D, that we could express the relative amounts of these at equilibrium This is a big deal. Notice those two words are almost always in that sentence, okay? We could predict the relative amounts of these at equilibrium if we knew the K. And K is the concentration of C, concentration of D, over concentration of A, concentration of B. It's really the activities. But we simplify this. We can simplify this down dramatically if we just call these the concentrations. That's what K is. That's a definition. So did you also remember that P of X is equal to the negative log of X? That's the P function, right? pH is equal to the negative log of the hydrogen ion concentration, right? POH is equal to the negative log of the hydroxide ion concentration, and pK is equal to the negative log of K. So pKa is equal to the negative log of the Ka. Right, I did that a little fast, but it's a video, so you can slow that down or stop it and go back and look at it again. So, if we're looking at an acid-base reaction, plus B minus, boom, boom, right? If we're looking at that reaction, then the K of this reaction, and we're going to call Ka because we're talking about an acid-base reaction. The Ka is equal to the concentrations of A minus times BH plus over AHB minus. Okay? Just by definition, we're going to take the products over the reactants. Well, then the pKa is equal to the negative log of the Ka. Right, so it's just the negative log of all that. All right. So the question then is, if we have, this is what we're saying, given a pKa value, predict the relative strength of an acid or a base. And so this becomes, I think we're ready to sort of just reach out and grab it now. Let's look back at this reaction here. Suppose we have a strong acid. If we have a strong acid, sorry, music. Listen to Pandora. That's a little tacky, I guess. So look at this. If this is a good acid, if it's a strong acid, would you expect there to be a lot? Or little of the product? Would you expect to be a lot of the product or a little of the product if it's strong? Okay? Alright, the answer is a lot. Now, if there's a lot of the product, would you expect, look at this, look at this expression right here. If the product is big, would you expect the Ka to be big or small? Think about that. Pause the video and guess. Is it big or small? If there's a lot of product, is it big or small? It's big, right? Because if we have a lot of product, that means we're going to have a little bit of this. That ratio is going to be big. Okay? Now the next question. If the Ka is big, is the pKa going to be big or small? I got someone at my door. Come on in. If the pKa is big, if the Ka is big, is the pKa going to be big or small? Take a second. Pause the video and come back and make a guess and then turn it back on. Okay? If the Ka is big, the pKa is going to be small. Take a calculator. Prove this to yourself with a calculator. Prove this to yourself. All right? That's all I want to do. Oh, I guess I do want to say one more thing. Give me a second here, Dylan. Oh, come on, sit down. I do want to say one more thing about this. That we're eventually going to do this. We're eventually going to take the pKa tables, which you've got in your packet, and we're going to look at a pKa, and we're going to evaluate based upon that pKa. Is that a strong acid or a weak acid? And that's it, right? We've got all these pKa's, and it looks pretty, I guess, confusing at this point. But when we use those a lot, we're going to get comfortable with them. So let me just choose a couple of there. Hydroiodic acid, this is the acid, and this is the pKa. I'd look them up with you right now, but let's save some time. It's -9. Hydrochloric acid, its pKa is -7. Acetic acid, its pKa is 4.8. Water, its pKa is 15.7. Ammonia, its pKa is about 38, maybe 35, something like that. Okay, really high. Methane, its pKa is greater than 60. All right, so if with just those alone, I think you can appreciate that the stronger the acid, right? These are even called acids. You memorized 6 strong acids in Gen Chem: Hi, HCl, HBr, H2SO4, HNO3. And perchloric acid, HClO4. These 3 all look the same. These 2 are familiar, and that one's nasty. Okay, so if you know that, you know these are strong acids, and that's negative. Obviously very much negative, right? Hi and HCl. And this is an acid because it's called acetic acid. This is not an acid. So you can see this is basically our baseline. That's around about the midpoint. Everything lower than that is acidic. Everything higher than that is basic. Or rather, not acidic. It's very weak acids. Okay, we'll talk about the context, the comparison between acids and bases later. But let's just speak in the language of acids here for this. Memorize this, or memorize something like that. Or better yet, you answer a bunch of acid-base questions using this pKa table, right? Hi. See, there's Hi is -10. Oops, wrong table. HBr is -9. Right? You see, these are really strong acids. And you get back to something like this. Hydrogen phosphate, that's actually an acid, right? But it's a pretty weak one because its pKa is 12.3. Okay, so that rounds out objective number 2. And as I said, I'm going to make a separate video for the remaining objectives for this lesson. Thank you.